the majority of you already have a account on our local supercomputer Hyades. If you don't, just come back later. Come back during this lecture, after this lecture, and I'll help you to create an account on Hyades. So this is the outline of my talk. So first, I'll briefly review the hardware architecture of the cluster. A little bit background of the hardware will help you understand, will help you optimize your code better so that you can take more advantage of the cluster. Then I'll show you how to access Hyades and show you the computing environment on Hyades. And then next I'll show you how to compile codes and running codes and how to do visualization and analysis. And last we'll have a Q&A session. But feel free to interrupt me and ask me any questions during the talk. So here we go. I guess every one of you is an astronomer, so Hyades is a star cluster. We always choose a star cluster for our cluster name. So the previous one was Pleiades, and Hyades is supposed to be the half sister of Pleiades, and it's also in astronomy term, Hyades is also a star cluster in a later evolution stage than Pleiades. So we sort of feel it's a lateral evolution of our Pleiades computer cluster too. And here is a quick summary of the hardware configuration of Hyades. We have one master node, which is a quad socket configuration. And we also have a Linux node. The salient feature of the Linux node is that it has a lot of memory. It has a half terabyte of memory, so it can run a lot of big memory analysis code very comfortably. And then we have the so-called type 1 computer nodes, which are the conventional computer nodes. It has only the pure conventional CPUs. And then to keep up the developing trend in the high performance computing area, so we also have a tiny number of accelerated nodes. We call them type 2. So the type 2A is type 2A computer nodes are accelerated by the NVIDIA K20 GPUs, which are the latest Kepler GPUs. And we were also very lucky to get a few Intel Xeon Phi donated by Intel itself. So I'll tell you a little bit about that. And then for the storage, we use a parallel file system called Lustre. So the total capacity of the Scratch storage is about 146 terabytes. And we are also very lucky that we got another donation of a 1 petabyte private cloud storage from the very infamous Chinese company Huawei. Okay, but then this one is in the testing phase right now. It's almost ready. We plan to release this for general usage pretty soon. So if any of the lecturer want to share their source code, so this is a good place, because this one actually uses the Amazon S3 protocol. So it's a cloud storage platform. Okay. The interconnect we use for our cluster is called InfiniBand. I'm not sure whether you have heard of that, heard about InfiniBand at all. It's a network fabric that is very fast. The generation we use is called QDR. It's 40 gigabits per second. And the really nice thing about InfiniBand is that the latency is really, really small. So for this product we use, the latency is 3 microseconds, 3 microseconds. So the conventional Ethernet, for conventional Ethernet, the latency is about a few milliseconds. So the latency of the InfiniBand is 1,000th of that of the Ethernet. So InfiniBand is the key component to make our cluster a supercomputer, not just a bunch of computers. So here I mentioned that. Okay, so now I go to a little bit detail of each of the hardware. So first we have look at the master node. The master node is a Dell server. It has 2 Intel Sandy Bridge class CPUs. So it's a quad socket system. So if you look at the right side, you see each CPU has 8 cores, and those 4 CPUs actually interconnected on the ring bus. The interconnection between them are called QPI. And one thing feature, one takeaway message from this one is that you see this is the so-called LUMA architecture, long uniform memory access architecture. So what that means is that so each CPU has its local memory banks, and then it has the other memory banks, right, are the remote memory. So the cost to access the local memory is much smaller than the remote memory. Okay, so I'll mention a little bit more about this. So yeah, this is the takeaway message. Okay, so this is our master node. Whenever you log into our cluster, you actually log into this node. So this is only this master node provide all the plumbing for our cluster, and you are not supposed to run any serious computation on this machine itself. You mostly just doing compilation and debugging of your codes, and then submit and monitor your jobs, etc. Okay. Then the next major component of our cluster is a thing called an analysis node. It's also the same 2U Dell servers. It also has 4 Intel Sandy Bridge CPUs. But the one really nice feature of that one, it has a lot of memory. It has 0.5 terabytes of memory, and also the hard drives is 2 SSDs configured in a RAID 0 configuration. So it's scraping. So the I/O on this thing is very fast. So it's designed to run visualization and big memory jobs. And then we have the so-called Type I computer node. That's the conventional computers. Only has CPUs. So each one. So this is a dual socket system. So each one have 2 Intel Sandy Bridge Xeon CPUs. So it's each CPU has 8 cores, and the clock speed is 2 gigahertz. And each one also has 64 gigabytes of memory. So it has so 4 gigabytes should be enough for everyone. Okay, so you should comfortably run your code. And we are also envision because we have a lot of memory here. So we also envision that we can also, if your application call for that, we can configure some of the memory as memory disk, so that when you need to dump a lot of code, you can when you do checkpointing, dump a lot of code, dump a lot of data, we can use the memory as memory disk to stage the I/O. So if you want that feature, let me know. Okay. Then we have this, as I mentioned, we're trying to keep up with the development. So we have a few accelerated loads. One type of accelerated loads is are those that are accelerated by the NVIDIA GPUs. So I'm sure some of you have tried CUDA programming before. So this is a good platform for CUDA programming. And if you're interested, I'll mention a little bit more. But if you really trying to do massively parallel calculations, so I think the industry expert actually recommend you to use different approach like OpenACC. So when you try to scale your code beyond a single box, right? You have to okay. And the second type of our accelerated computer nodes are those that are accelerated by the so-called Xeon Phi. I'll give you a little bit. I'll introduce you a little bit more about this Xeon Phi architecture later. So here is more details about the Intel Sandy Bridge Xeons. So you'll see that so each CPU has 8 cores. But Intel has a technology called hyper-threading. So if you enable that, it will have 16 threads. So each CPU, so each physical cores will appeal to the operating system as 2 cores, 2 logical cores, if you enable that. So that's and it also has a feature called turbo. So if you only run a single serial job on that one, the clock speed actually can push from the base clock speed 2 gigahertz to all the way to 2.5 gigahertz. So you can get a temporary boost about that, and it has that amount of cache. So if you really want the best performance of your code, you would worry a lot about the cache coherency, cache miss, things like that. And also, you can see that this is also similar to the quad-core system. This is also a Luma architecture, right? It has each CPU has its local memory banks, and the bus between the CPU are the so-called QPI. Here I give you some numbers, right? The QPI, the bandwidth of the QPI is only like 16 gigabytes per second, right? But the total memory bandwidth is actually 51.2, right? So here is clearly shows you it's much cheaper for this CPU to access this local memory than access the remote memory through the QPI links. You should have this in mind when you design your code. Okay, but then to really take advantage of this code, you really need to use this the vector unit on the CPU system. So over the years, Intel actually has a lot of vector technology. Initially, it's called SSE. So AVX is the latest generation. So this one is a 256-bit wide vector unit. So it means actually it can do 8 double precision flops per cycle. It might be puzzled here a little bit because a double precision number is actually 64 bits, right? So 256 divided by 64 would be 4. You would think that it can only do 4 double precision per cycle. Does anyone have an answer why it can do 8 double precision here? Okay, the reason here is actually because a so-called instruction called FMA, it's fuse, multiply, add. So which means so on any single clock cycle, you can do A plus B times C at one single press. So at one single clock cycle, you actually does a multiplication and addition. Okay. So that's why you can do 8 double precision for per cycle. All right. So here is also a quick summary of this the latest NVIDIA GPU based on the Kepler architecture. So each one of them has 2,496 CUDA cores, but but only 1/3 of that is can do, but only 1/3 of that double precision unit. So this actually, so this also gives you some constraint on the CUDA performance, GPU performance here, right? The core speed here is also about 700 megahertz. You can do a quick calculation about the double precision performance, right? You calculate the clock speed here and double precision units, because each double precision can do one double precision, but here it's also a 2. The same reason. They count a fuse multiply and add. They can do a fuse multiply and add at 1 clock speed. So that's how you reach this number. Okay, but you can see that if you can control your precision, or you don't worry about your precision very much, you'll be much better off to use single precision numbers, single precision floating numbers, because you have a lot more CUDA cores. Each CUDA core can do single precision numbers. So that's a factor of 3 speed up. Okay, here you can also see the interesting is that so each CUDA, each GPU actually has its local memory. The local memory bandwidth is a lot higher. It's not higher than the CPU memory bandwidth. Okay, but then the connection between the CPU and GPU is through the relatively slower PCIe link. So you can calculate the PCIe speed here. So it's a huge factor. So when you're trying to program for this kind of architecture, right? You really want to minimize the data transfer between the CPU and GPU. You want to transfer the data once, and reuse the data multiple times on the local GPU. Okay. So here's a block diagram here. You can see there are a lot of simple CUDA cores, but for every 3 simple CUDA cores, there's only 1 double precision unit. Have this in mind. Then here is also a quick summary about the Intel Xeon Phi. Intel Xeon Phi was Intel's answer to GPU computing. The approach their take is that they don't use a lot of simple cores. They use a much heavyweight conventional core. So they only have 60 cores. 60 cores, but those are more or less equivalent to the Pentium 2, which was released about 10 years ago. So it's simplified cores. It's in order, dual issue. But the nice thing about this thing is about that they also have 4 threads per core. So if you actually they actually each. So those things actually running a Linux by itself, you can actually SSH into that thing. So if you look into that, if you actually log into this Xeon Phi, you'll see 240 CPUs. Yeah. Okay. So the core speed is a relatively simple architecture, and the core speed is compared to Xeon's is relatively slow, but it has a lot of cores, and also they double the vector unit width to 512 bit. Okay, so again, to get the best performance from this architecture, you really want to use the vector unit. Okay, and you can also do a quick calculation, right, to reach their claimed theoretical flops, which is 1.01 size order. You can do that, and also. They're also doing some tricks, right? You really want this FMA to get the maximum performance, but your code may not be able to arrange for that, right? Then you say, okay, also similar to the GPU, so each Xeon Phi also has its local memory, right? So the local memory bandwidth is a lot higher than the CPU memory bandwidth, but again, the communication between the CPU and GPU are through the very slow PCIe link. Right, have that in mind. All right, this is the block diagram. They put, okay, so they actually, for the Xeon 5, they actually put all those simple Pentium 2 level cores on the RIM bus, right? They also have some implication, right? If you want to do communication, so this core, it would be much cheaper for this core to talk to the next one than another core halfway through the RIM. Okay, so there's a lot more going on in the hardware side. How best to take advantage of the hardware. But I'll just give you some quick take-home message. So the first key to performance is vectorization, as you can see that, right? So if you don't use the vectorization for the conventional Intel CPUs, right? At most you can do one flop per cycle. But if you use the vectorization, you can do 8, right? So here we can do a quick calculation, quick exercise to calculate the theoretical peak performance of our cluster. So we can see that the peak performance of the Intel Xeon, which used in our computer nodes, is 128 gigaflops. So all the Xeon 5s will give us a peak performance about 48 teraflops. So if you don't use any acceleration at all, that's the maximum you will get. And the peak performance of the NVIDIA GPU we use here is slightly more than 1 teraflops, and the Xeon 5 is also about 1 teraflops. If add everything together, you would get that. But you would be extremely lucky, or you would be a genius to actually get this number. Okay, so another key to performance is really about the data locality, or about communication avoidance, right? We can see the one. If you we can calculate the bandwidth for the CPU. If you do this simple calculation, is this number. If we scale this as 1, right? Then the memory for this kind of architecture is this. So the memory bandwidth is 160 times slower than that one. So if your code is memory bound, so for every calculation you have to grab the data from the memory. You'll be running 160 times slower, right? Then there's also the limit about this Luma architecture, right? This is more important when you have a multi-threaded code, OpenMP code, for example. So the bus link between the two CPU, the bandwidth for that one is only 16 gigabytes. So in the worst case, right? In the worst case, if you're already memory bound, you access your local data, which is 106 times more slower. So if you have to, for some reason, you have to access the remote memory, which will make your code even slower. Then sometimes when you okay, so and this PCIe speed is also the bandwidth is also much slower, which is very important because both the GPU and the Intel Xeon 5 communicate with the CPU through the PCIe link, and also we're talking about a supercomputer. We're doing a lot of messaging passing between the nodes. So the InfiniBand I just mentioned also happen to reside on the PCIe bus, right? So if for every single calculation you have to transfer the data through the network, the best you would get is 4 gigabytes, right? So which may be slower. But then if you have to for every calculation, you have to do some I/O to the disk. But we have some really fast SSDs for the big memory system. But even that is almost 16. It's more than 16,000 times slower. So consider that. So if you do a lot of checkpointing, plot files, this is what you can get. And SSD is 5 to 10 times faster than the conventional CPU. So there is a trend in the numerical industry to trying to develop the code or library to try the best to avoid communication. Okay. All right. So given our cluster, so what kind of application will take advantage of the cluster? So we really want to run, because you're here to learn supercomputing. So we really want to run the massively parallel jobs. But conventionally, only a few years ago, which means just pure MPI jobs. You start a lot of MPI process and talk to each other, pure MPI jobs. But then we realize, given the architecture limitation, we realize that you see that because the memory cost, the memory access cost here. So nowadays, we really recommend you to if possible, to convert your code to a hybrid programming model. Is that you combine MPI to OpenMP. In that case, on this kind of architecture, you only start, instead of starting like 16 MPI process per node, you start like 2 MPI process, right? One per NUMA node, one per CPU. And then you, for each MPI process, you start like 8 threads, 8 OpenMP threads or POSIX threads here. Given the number I showed you before, this can really take advantage of for this kind of cluster, right? Then obviously you can run multi-threaded job like OpenMP, POSIX threads, and a lot of our users also running embarrassingly parallel jobs, which means they have their codes are serial codes, but then for the same codes they have a lot of data. They have a lot of data. They want to run the same code on like thousands or more data. So they can start around, unless they can run serial jobs, right? Or people also doing visualization analysis, and we're also venture into some big data calculations. We can do Hadoop. So if you want that, let me know, and we also have a bunch of accelerating nodes, so we can do GPU computing and microcomputing. By the way, if you already log into a cluster, you don't see those because we are in the testing phase of that. But we welcome your feedback. So if you want to try those, let me know. Okay, so hopefully by now, every one of you will already have access to Hyades. But if not, here's just a quick recap. So only SSH is not. So we only have 2 public hosts. One is the master node called Hyades. So you use SSH, and we also have this big memory analysis node called Eudora. You have essentially, if you use password, you use the same password, or if you use SSHK, use the SSHK to access the same those 2 nodes. And because we are really short on time, so this time we essentially use SSHK. Everyone uses SSHK for authentication. So this is how you create that one. If you haven't done so, right? So you go to your .ssh folder, right? Then you generate key. Here I give you a little bit more options than I send in the emails. Basically, you want a SSH key that's big enough, and also the type is RSA. If you run this command, it will generate 2 files. One is one is Hyades. One is Hyades is private. This is the private key. You really want to keep. You do not want to share this private key with anybody else. And you also another one is a public key. It's called Hyades.pub. You should send me this one as an email attachment. Once I upload it to you, then you can, instead of using password, then you can use this key to authenticate into Hyades or Eudora. Okay, so here is a time-saving tip. If you configure that, doing some add those standard into your SSH config, then you can simply log in at this. All right. Sorry. Okay, so once you are in, you will see you need to get familiarized with our computing environments. So we have two storage space, which are mounted on all the nodes on Hyades. One is your home directory. It's which is a NFS mounted system, so it's relatively slow and has a limited capacity. So this directory is only intended for storing your source code configuration files. It should not run any simulation from that directories. And for your simulation, it should run from our user work directory, which is a raster, which is based off the raster file system. Raster is a parallel file system. It's almost universally used at every supercomputing center. So each one will have a work directory called PSF, your username. For example, for myself, it's PSF DOM, and then in your home directory you have symbolic link PFS. Will go there. It has a total capacity of 146. Right. You should run your simulation from here. And if this is your first time to use a supercomputer, you'll learn that as almost everybody else, we use a utility called module to manage the environment and software. So to list this one, maybe I'll do you a quick demo. Okay, here. Okay, so here is, for example, the same thing. If I want to log into Hyades, right here, right? So so here you would see I have, as everybody else, I have this link to the raster file system, and module list will show you some of the modules, some of the environments that's already set up for you. So so to save everybody time, so I already set up some default system. Since this is the cluster, we already have this Intel MPI for the MPI implementation. If you want to run any MPI jobs, it's here, and we also have this Intel compilers right here. And then, if you want to know what software are available on our system, you would do a module avail. To show you a lot of tools and growing. So if you need some special software, just let me know. So I can create it and create a module file. Then everybody else can share it. For example, so I'll show you some tricks. So for example, right now, I didn't load any Python modules. So the Python would be the stock Python provided by Red Hat. So if I do a Python version here, so it's 2.6, right? Then if I already show you, we have some Python, right? Python module avail. A lot of people running Python, so we do have here. I'll have these two Python modules. Okay, so if I do a module node Python, okay, so here you notice something like that. You notice for some of the module you have this default, which means because we have two versions of this Python module here. So if you can do some Python 2.7 to load that, or Python 2.6 to load that. But then since 2.7 is default, so you don't need to type this. So if you only do that, you load that module. So let's double check it's loaded. So you can see that Python module is right here, and let's double check it's here. So yes, so you can see this is on a different directory, right? So it's different directory here, and if you run Python version here, it's 2.7.3. Okay, so this module has a lot of you can learn a little bit more about that one. So you can do module help.
One more piece about module run.
Pardon me?
You corrected it.
Sorry. Yes, I know. Yeah. If you do this right, tell you. So it tells you what it does, and you can also. Will tell you exactly what it does. Essentially, it's just this is the license to manipulate the environments. You can do the same thing with Bash, right? You can, if you do Bash, you do export Python path, blah 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 blah, or export path, right? If you are using C shell, you do set env, set environment, things that. But the nice thing about this one is it's global. Once I set up this, it will work in any possible shell. Okay. And I just want to mention, so I already compiled a lot of tailor-made Python module for that. I know a lot of Python users. So if you load this module, you will have tons of Python tools like SciPy, NumPy, MPI4Py, Matplotlib, something like that. All right. So this is how I do it. And also, if you although we recommend you to use the Intel MPI, right? But then somehow you don't like that. For example, you want to use Open MPI. This is how you do it, right? So this in one step, it will unload this module and load this module, right? So you totally unload the environment for the Intel MPI and load every environment for the Open MPI, okay? You can play more with that. You running all those commands. Okay. Oops. All right. So on our system we have compilers, right? We have the Intel compilers, PGI compilers, and GLUE compilers. And Intel, as you see, is the default. It's already loaded. And in our experience, we found the Intel compiler is often at least 2 to 3 times faster than the GLUE compilers. And PGI compiler is also excellent. But we are mostly interested in its capability to do the GPU computing. So that's why we have it here. So if you want to use PGI, you can swatch that too. And for MPI implementation, we have quite a few, and we plan to compile and install more MPI options. So if you have some special need, let me know. But then the default and recommended MPI implementation is the Intel MPI, which I personally like a lot, which should have you covered. But if you code behave somehow strangely that don't work well with Intel MPI, you can try the other MPI implementations. Okay, here I show you how to, given the default configuration, how would you compile codes? For serial codes, it's easy. If you haven't used the Intel compiler before, the command for C compiler is called ICC. So for GLUE compiler is GCC, right? So for C++ is ICPC, or you can use the same ICC, it's fine. And for Fortran is iFort. Okay, and how you compile, it's just same. I'm sure everyone has compiled code before, but there is the compiler option is a really big topic. You really need to consult the online documentation. We have some recommendations. So again, as I showed you before, to really take the best advantage of that, you want to use the vector unit of the Intel CPUs. And to compile OpenMP code, you add one more option, OpenMP here. And if you want to compare the pure MPI code, right? The pure MPI code, no multi-threading. Okay, then you, instead of using ICC, you use a wrapper called MPI ICC, or MPI ICPC, MPI iFort. MPI, those are just a wrapper, because if you are really adventurous, you can actually use ICC, but then MPI implementation just provide the libraries and the startup script. If you use ICC, then you have to add a lot of options. You have to specify where the library is, how do you link it, what option to use. So here, this wrapper save you all the trouble. So I recommend to use that. But if you really want to load the gory details, there's an option. You can run MPI ICC -show me. It will show you all this option to use. So you can use conventional ICC to do that. Okay, here as I said, the recommended programming model is for this kind of architecture is a hybrid programming model, which use MPI between the Newman nodes and OpenMP inside the Newman nodes. So to do that, you add one more option. So this option MPI is to use a multi-thread MPI, which means is a thread-safe MPI. So that a lot of global variable will not be messed up. Okay, safer. And since it's also a multi-thread code, you also have this OpenMP options, just like that. And to running our code, okay, so if this is the first time you use a supercomputer, you realize that unlike using your laptop, you don't directly run the command. You don't directly run like Firefox, right? You actually submit your jobs to the resource manager, and then let the resource manager to find the best resources for your code. You may not get the instant satisfaction, but this is the best way to use the resources here. So for our system, we use Torque as our queuing system and resource manager, and we use MAUI as the job scheduler. Here are a few commands and utility you will most often use. You use QSub to submit your job. I'll show you more details here. And once you submit job, you want to know whether it's already running or not, right? You use QStat to check the status of your jobs and everything. And if you somehow change your mind, you want to kill your job before its completion, use QDeal, right? There are more commands. I'll add more to our wiki page, and also MAUI also provides some other utility that might be useful to you. And one thing is called showqueue. Showqueue is more or less equivalent to QStat, or show you the show you both the active and idle jobs in the queues. And this is a really nice tool. It's called show backfill, right? So oftentimes, for example, in our class we have about 3,000 cores, right? So if already people are using 2,500 cores, right? Then if you want to start a 600 core job, you cannot, because there's not enough resources. But if you use show call, show backfill, it will tell you, well, we only have 500 cores available right now for maybe 10 hours. You can adjust your resource requirement, right, to only request 500 cores instead of 600 cores. Okay, so this is used. And check job is also less tool. If for some reason your job got stuck, you wait in the queue for a really, really long time, you want to run check job, your job ID, then that will give you some idea why it gets stuck or some other errors. Okay, so on Hyades right now for the type 1 computer, we only have 2 cores, 2 queues. One is this one is so-called normal queue and hyper queues. As I mentioned that, so each Intel Xeon CPU can do 2 threads if you have this hyper-threading enabled. Okay, there's a big debate whether we should have hyper-threading enabled or not. I think on your laptop, hyper-threading is enabled by default. So, for example, I think my laptop actually has a CPU that has 2 physical cores. But if I look into the CPU status, you will see 4 cores to the operating system. Okay, but since
so Don, you have a typo there under 32 cores. Is that
which one?
enabled, not disabled?
Oh, sorry. I'll change that. Yes. Naively you think in the high performance computing environment, because we are already pushing the limit of the CPUs, right? You would think we should not have the hyper-threading. We should have it disabled. Because if you are running the CPU at maximum speed, right? But in reality, I found out that for most of the real world applications, it would be really lucky to actually push them. So we found that for at least for some of the code, it's beneficial to have this hyper-threading enabled. Okay, so in that case, this give you cheaply double the core count. So if your code, you should run your code. If you run your code on both the normal queue and hyper queue, and see whether if your code runs about the same speed on both queues, you should definitely use that, because that saves more resources here. Okay, so but we are experimenting. So we right now we set up like 2/3 of our nodes with hyper-threading disabled, but 1/3 enabled. So try both. But then I'll get into this later. So if you when you are submitting your jobs to the torque queuing system, you would use this option. This -q means Q normal, and here you will see if you want 64 cores, here you will see I want 4 nodes, right? So each node has 16 cores, processor per node 16, right? So here's Samsung 32, and here's a sample PBS script for MPI jobs. I have this annotation here. So here, the first line tells you what kind of, essentially, oh, by the way, all those PBS script is actually just like your conventional shell script. You can either use bash or C shell, whatever you prefer. But here, let's just use the default bash shell. So the first line tells you what kind of shell it uses, and it's always nice to give it a distinctive name. So we call it, our job name is called hello. Okay, we're using the normal queue. We don't use hyperthreading here. So here we're requesting 64 cores, and we request a total wall time of 4 hours. If your job doesn't finish in 4 hours, right, the job schedule will kill it. Okay, so specify that. So you can also add in this option, right? You provide your email. So here it says, I want the queuing system to send them email when the job A means aborts, B means beginning, starts, and E means so whenever your job gets to run or finish or fail for some reason, you have an email for that one. So here, in that one, so here, this is very important, right? Suppose you really do that. The reason for that is one. So you are actually when you submit your job, you're actually on the master node, Hyades, right? But when your job actually get to run, when this script actually get to run, it will be running on one of the computer nodes. So when it actually gets to run, it starts from the home directory, right? But in your home directory, but your code can be, for example, in the raster file system in PFS, right? So this one will just change that. The PBS will save your current directory into this environment variable. Then when you run this, when you cd that, it actually goes to that. Let me do it. Maybe just give you some quick idea of that. So if I go to PFS, right, I have a lot of codes and jobs here, right? Then if I do a Q sub something, MPI something, right? So here's the important thing is that you notice that my current directory is actually here. So so in your PBS script, I have a lot of things that if you don't have this line, it will start at your home directory. Then when you finally trying to run this thing, it will not be able to find this executable because you are in your home directory. So you must have this one to change, or you can explicitly change. So do something like cd PFS DOM, so go directly to that one. But this is a nice feature here. All right. Okay, so then since this is then you go to that work directory. Since this is the MPI jobs, right? So you always use this. This is more like a startup script. You use that to start it. Right, this is your code. You compile your code as I showed you before, and this show you the on how many MPI process you want to use. 64 in this case because 4 times 16 is here. Here, the nice thing about the Intel CPU is that you can compile your code, and then your code can run on any kind of network fabric. So you can choose it. You can run on InfiniBand. You can run on shared memory. You can run on Ethernet. So here's the way. Since this is more or less network agnostic, so you have to specify what kind of communication medium you want to use. So here in this case is shared memory and open fabric for InfiniBand.
So where is the host file?
Pardon me?
Host file. Where is the host file for MPI?
Which host file? Which is the host file?
I don't know, but how MPI is no where is each node?
Oh, where is each node?
Yeah.
I'll show you. I'll give you a topology of our cluster later. If you want to see, oh, by the way, if you are interested in seeing our cluster in action, let me know. We can arrange a tour of our data center. Then you have a much better idea. I'll show you later. Okay, can we talk offline? Okay, here's an. Okay, then essentially you put all those. This is the shell script. You put all those content into a file. You can call it whatever you want. You call it MPI PSUBs, right? Then you submit this job with QSUB, right? Then if everything's okay, so your job will eventually get to run. Well, then in that case, you will provide, you'll produce a lot of results. You also in our case, you will also have some files like that. So, so if your job, so yes, so if you call your job name as hello, right? Eventually you will have a hello.o, which means this is the standard output of your job. You also have another file called hello.e, which is if there is any error. So the standard error will be redirected to that file. Something like that. You'll see it. All right. Okay. Yes.
When it's, for instance, 64 cores, like the example you have here, do you have to ask specifically 4 nodes with 16 cores, or the job could be spread over, I don't know, 60, maybe 64 nodes?
Yes, you can certainly do that, but this is not the this is recommended way. So if you want to run a 64 core jobs, right? If you do something if you do something like nodes equals 64, ppn equals 1, then in that case, right? Then in that case, possibly your job will actually be spread to 64 physical nodes. But do realize the bandwidth hierarchy I showed you before. It's much more expensive to communicate through the network. So if you actually do that, right? So there are 16. So there are 16 MPI process per node. And between them, they don't use network to do the communication. They use shared memory. So memory is a lot faster than even the fast InfiniBand. Make sense? Okay. So here is also a sample script for OpenMP jobs. OpenMP again is a multi-threaded job. So in that case, there is only one, in Linux terminology, right? There is only one process, and like either 8 or 16 threads. They share the executable, they share the global data, right? This is how you share the memory. But the downside for OpenMP is that it cannot go beyond a single node. So you have to do this multi-thread inside a single node. So this is the limitation here. So again, we use the same thing here. I'm so sorry. This is a typo. I should update that. So you can this should be nodes equals 1, because this one you cannot go beyond a single node. Or simply you can do something like that. You can do NCPU equals 16, right? Then doing the same thing here. But then with OpenMP, you need this environmental variable to control how many threads will be started by the operating system. Right? You use that. That depends on your code, right? I know, for example, the MESA, the stellar evolution code, somehow cannot does not scale, although it's OpenMP code, it does not scale really well, right? It probably best can run at most like 4 cores. So you want to control that to 4, something like that. So you run this. And as I said, the recommended programming paradigm for this kind of cluster is a hybrid job, right? Hybrid programming. So OpenMP plus MPI. So it's slightly more complicated than that. So again, here we request 64 cores, but in that case, we do that too. But here we worry. Let's not get into the gory details. But those things essentially controls the data affinity, right? Exactly as I mentioned before, the local memory is a lot cheaper than remote memory. So essentially, you want the memory to be local, essentially here. So then there's 2 more options here. So in that case, because we are starting, so in that case, we want to start a MPI process per Newman node. So there will be 2 MPI process per physical node. This means PPN is 2. And in that case, so since there are 4 nodes, so there will be 8 Newman nodes. So 8 MPI process here. Does it make sense? Okay. So there is also, I know a lot of people, although we don't encourage that, but I do know a lot of people want to run serial jobs here. So this is how your serial jobs is much easier, right? You only request one single CPU, and it's more or less how you would run a serial job here. Don't need to run a wrapper. But often case, people do run serial job, but they run serial job in a different fashion. They are doing the so-called embarrassingly parallel jobs, right? They have a single executable, but they have a lot of different data. So you probably would want to run hello 0 as the input, hello 1, things like that. Given that scenario, right, you can take advantage of one feature in Torque. It's called job array. So in that case, the difference between this one and this one, you have this feature called -t from 0 to 31. I also, for education purpose, I add this feature. This means you would actually merge the standard output and standard error into one file. So instead of having this hello.o, blah blah, hello.e, blah blah, you will have only one file called hello.o, things like that, right? You'll scratch that. So here the sense that this environmental will automatically be translated into 0 to 31. So here, instead of 1, you automatically submit it to 32 jobs. So this in parallel programming parlance, this is more like So this trick does the automatic parallelization for you if you have a very simple user case. Okay, and then again, once you run your simulation, you probably have a lot of data to be visualized or analyzed. So this is how we do it. So Eudora is our dedicated viz node because it has a lot of memory, and this is how you access it. So in your case, we use the same SSH key to log into that, same thing. So if you want to do that, so we add this feature because a lot of visualization tools are X11 tools, right? You want to enable X11 forwarding or trusted X11 forwarding. So dash Y is trusted in our forwarding. So you can do that, or you can put all those options into your config file. The entire case you can do things like that. And we have a bunch of viz tools on our system. It's, notably, there are Visit, YT, IDL, Python, things like that. And if you need anything else, let me know. So that's it. And I'll leave a lot of time for question and answers. But you probably already know that we have a very rudimentary wiki page because I haven't updated for a while because we are very short-handed. But this is a good opportunity for me to update the file. So ask me a question. So I'll know what you want so that I can update the wiki and everything. Okay?
All right, and Shaw will be hanging around for a while here in case anyone is having trouble with their accounts or anything like that. But if anyone has more general questions as opposed to I can't log in or something like that, please go ahead and ask them now.
Yeah, this is a very basic introduction. So for the advanced user, you will be really bored. But if you have more advanced questions, I'm happy to answer to try my best.
All right, well then, oh yeah.
This is actually kind of unrelated, but is there some repository space for
That can be arranged. What repository do you want? We have a Git repo if you want to use. Yeah, you want that? Or we can. The way we can do that, I do have a personal Git repo on the server. I can give you access to that, or we can set up a shared directory. Right, so it's more or less a public directory. Right, we can share the data, whatever you want.
I don't care about it.
Okay, let me know what data you want to be available to the users. I'll do that. Yeah.
Do we have a quota of this disk space?
So far not, but I would guess we have more than 50 people. So if everybody uses a lot, that will be a problem.
Behave well and we won't have to.
We have. Let's not worry about that for long. So my philosophy is that this is the tool, right? You want to be productive. So try to maximize the usage, unless somebody complains. So if somebody complains, don't be angry, right? It's okay. So it's just a tool.